Hi, this is Anjana Vaslan and welcome to the demo for my personal project, Multi-Material 3D Simulations of an 8-Vane Magnetron. 4 major steps were completed in order to execute this project. First, I disassembled a commercially available Magnetron, and then I got some physical dimensions to start my initial design. I performed design calculations that were developed with the guidance of research papers and textbooks, and I used this to create a 3D model in Fusion 360. I performed simulations using this 3D model with different materials in CST Studio Suite. So let's get into the disassembly process. Here you can see me taking apart an LG Magnetron. Prior to actually reaching this step, I had to verify with LG that it was safe for me to take apart. So I took off the plates that enclosed the housing and I detached the oscillator from the electrical connections. I then removed the magnets and washers, and I was able to pull out the oscillator with fins attached. After removing the fins, I used a Dremel to dissect the Magnetron. Here you can see a cross-section of the Magnetron that I dissected. The parameters that were most important to me was the anode inner diameter, the inner and outer rim diameters, the cathode dimensions, and the vane thickness. The strapping ring dimensions were also recorded. These parameters were used to determine the applied voltage and the applied magnetic field for the design. This can be seen in my design calculations. Here's the basic Excel sheet that I used to guide my design. I designed for 5.8 GHz instead of 2.45 GHz, as I came across research that utilized this frequency for solar power satellites. My calculations resulted in me choosing a B value of 0.08 Teslas and a voltage of 4.4 kilovolts. While I was 3D modeling, I started off with a strapped Magnetron, but quickly realized that this is not feasible for when the Magnetron needs to be printed using a DED printer. So I switched to a simpler model that did not have strapping rings or recessed vanes. This is the final model I used for the simulation process. There were 2 main types of simulations performed, the first of which was eigenmode analysis. This is a cold test of the Magnetron to verify the operating frequency and the mode that the Magnetron operates at. Here, I'm basically setting up the eigenmode solver in CST Studio Suite. I tested 3 different materials, a perfect electric conductor or PEC, copper, and aluminum. Let's take a look at the PEC material first. So the vacuum is what's being simulated here, and the background is set to whatever material is being evaluated. If we look at the electric field, we see that the vectors change directions in alternating cavities, which verifies that it's operating at pi mode at 5.764 gigahertz, which is very close to the 5.8 designed for. Now, if we look at copper, we see similar behavior, but at a slightly different frequency of 5.752 gigahertz. Looking at aluminum, we see that the electric field shows a little bit of overlap into the vane area, but it's very minimal and the frequency is comparable. Now, the next simulation performed was particle tracking. This was used to verify the applied voltage and to ensure that the design allowed for electrons to stay within the interaction space. So if we take a look at PEC phase, we see that the full Magnetron was simulated and the space between the anode and cathode was set to be the vacuum. The trajectory plot of a single electron showed that for PEC, it stayed within the interaction space at 4.233.58 kilovolts. And if we look at copper, we see that very similar behavior occurred at the exact same voltage. Looking at aluminum, we see that the electrons remain in the space at 4.2 kilovolts, so slightly lower voltage, but still comparable.